Hi, my name is Dennis Angel and I'm an XRPL developer at XRPL Labs, and today we're going to be talking about the SHAMAP. The first thing we're going to be talking about the SHAMAP is the architecture. SHAMAP is a hybrid data structure that manages the properties of a Merkle tree and a radix tree. This combination is designed to efficiently organize, verify, and synchronize large collections of data in distributed systems. So the Merkle tree principle is where each node contains a cryptographic hash summarizing all the data beneath it. This enables rapid comparison of entire subtrees. If the two nodes have the same hash, their subtrees are guaranteed to be identical. The radix tree principle is a tree organized so that each step down corresponds to a segment of a data's item key. This allows for efficient navigation, insertion, deletion based on keys. Together, these principles provide strong data integrity and high operational efficiency. So the next part is the node types. The SHAMAP is comprised of two main node types: inner nodes. These serve as the tree's branches. They do not store actual data, but instead references to child nodes and maintain a hash summarizing all the data within the child node. And then we have leaf nodes. These are endpoints of the tree that contain the actual data items. All leaves in a given SHAMAP are the same type, ensuring uniformity. The next part is traversal. Traversal is the process of navigating through the tree to access and manage the data. We have key-based navigation. The structure allows efficient movement through the tree using the key associated with each data item. Each segment of the key determines which branch to follow at each level. And efficiency, this design ensures that operations like lookup, insertion, and deletion are performed quickly, typically requiring only a small number of steps relative to the size of the data set. We have synchronization, and synchronization ensures that multiple copies of the tree can be brought to an agreement with minimal effort. So we have hash comparison. By comparing the hashes of the root or each subtree, it is possible to determine instantly whether two trees or subtrees are identical. And this allows for efficient updates. So if differences are detected, the structure allows for a rapid identification of exact points of the divergence, so only the necessary data can be changed. We have proof generation. So SHAMAP can generate cryptographic proofs about the presence or absence of data. We have inclusion proofs. To prove a data item is present, one can provide the path to the root of the tree leaf, along with the hashes of sibling nodes at each level. Anyone can verify this proof by reconstructing the root hash. And then we have exclusion proofs. The structure can demonstrate that the data item is absent by showing the path where it would be along with the relevant hashes. The next part is state management. The SHAMAP supports both mutable and immutable states. So an immutable state is where it cannot be modified. Most of the time the tree is not modified. This immutability ensures that once a state is established, it cannot be changed. And then we have a mutable state, which allows for changes. So when changes are needed, a mutable copy is created. Modifications to this copy do not affect the original, allowing for a safe concurrent operations and easy rollback if necessary. The next part is serialization formats. Serialization is the process of converting the tree into a format suitable for storage and transmission. So we have a compact representation of this. The tree can be serialized in a way that preserves the data structure and the hashes, allowing for it to be reconstructed exactly as it was. And this allows for interoperability, which enables the tree to be stored, transmitted, and shared between systems. One final point, we have the thread safety. So in environments where multiple processes may access the trees simultaneously, thread state is essential. So immutability for safety. Immutable trees are inherently thread safe, and no thread can alter the structure. And finally, we have interactions with caches and storage. So the SHAMAP is designed to work efficiently with both in-memory caches and persistent storage. So caching, we frequently access nodes kept in memory for fast access, while less used nodes can be evicted to save resources. So we use persistent storage. Nodes can be stored on a disk or a database, allowing for the tree to scale to a very large size. And then we have shared ownership. So nodes can be shared between different versions of the tree, reducing duplication and improving efficiency. In summary, the SHAMAP is a robust data structure that combines the cryptographic integrity of Merkle trees with the efficient navigation of a PF radix tree. Its design enables fast synchronization, efficient proof generation, and safe state management. These properties make it ideal for distributed systems that require both high performance and strong security guarantees. Thank you.